Right? This actually looks kind of like a figure we looked at in on Monday. And back here, it's kind of a spatial figure and a time figure. So back here would be like the beginning of time, the singularity, okay? And we're going to be talking a little bit about what physicists or astrophysicists know about the beginning of our universe. One of the things that's important about the beginning of our universe is, and it kind of reminds me of what Galileo saw, imperfections on the moon, right? The moon wasn't as perfect, the sun wasn't perfect. And actually the space that we call our universe had to have some like little, they're called perturbations in it, some small fluctuations that would ultimately become galaxies and stars. Okay. We're going to talk a little bit about, and actually I have a quiz question, I just made it up just a few minutes ago, it's the last slide here. And this number, if you want to put, circle it or whatever, that's going to be the years I'm looking for. So I think in my, instead of 37,000 years after the Big Bang, I think my slides say 380 instead of 375, 380. So 380, 375, 1,000 years after the Big Bang was the time, it's going to be on your test, when matter settled down to the point where energy could freely roam around. So that's going to be on your test, that years after the Big Bang. So if we kind of look at the fabric of space and time being created, actually this is going to be what we call inflation. It's a crazy time, and astrophysicists, they can say it happened. I don't know if they can necessarily see exactly how it happened, but basically we know the universe is expanding. Its expansion is accelerating. We know that, but early on, the universe went from being this big to being this big. Okay, it's called inflation. You can see there. You can see the fabric of space and time expanding. Okay. The first stars, it took a little while for our universe to cool down before stars could form, okay? And then within those stars became organized, or the galaxies that those stars were in became developed. We have planets be able to form, okay? So expanding, okay? And this is one of, we're going to see actually there are 3 gizmos. Does it look like a gizmo? Does it look like a spacecraft? There are 3 spacecraft that have actually been devoted to looking for signatures of conditions that cosmology, the beginning of our universe. So this whole time here, actually, and this didn't make it to the test, it might have made it to an earlier test, I'm not sure, but how long did it take from the Big Bang to now? And you're looking at 13.7, 13.8 billion years. Okay, between the Big Bang and now. So that's kind of in a nutshell. So we're going to talk a little bit about the details there. So yeah, I see in the caption here, it said 375, 380,000 light years. All right. So Big Bang, anybody in here watch that show, The Big Bang? Good stuff, right? Okay. So you might be like, how do we know anything? In a little bit, it's kind of like going backwards. Oh, by the way, so I don't forget. As I was debating whether I would need to go to the office from here, and I was debating whether I want to walk outside to go to the office or walk around, and guess what I did? I looked at the flagpole to see what the flag was doing. So in other words, I didn't have to go out and see if it was windy. Now, the flagpole can't tell me if it's cold or not, but I didn't have to go outside to see if it's windy. I just had to look at a flag. And that's kind of, I know, it's like, what's the stretch? But that's kind of what we would do with dark matter. We look at the influence, in this case, the wind, as on the flag, the influence dark matter has on the way galaxies dance, the way stars orbit the centers of galaxies. Okay, the way gravitational lensing occurs, yeah.
Okay, so it's been proven that time used to go faster.
Okay.
Like, we used to,
the Earth used to spin faster.
So like,
right.
The days weren't as they are now, maybe it was like 24 hours. How can they sit there and say, like, it's, okay, 13.77 billion years ago, when they don't know exactly how fast, how time was back then?
The time of the Earth spinning, and that's kind of a physics thing. The Earth has slowed down. It used to spin a lot faster. But you figure when they're talking about these years, that's relative to the way light travels now. So, yeah, I don't know if that helps, but it has nothing to do with an Earth year.
Okay.
But yeah, I think I know what you're saying. Definitely some unknowns out there. Yeah. So that little thing that we're going to call singularity was the blob, and the blob was very, like I'm reading scripture, but the blob was very hot and very dense. So we've looked at some graphs throughout the course of this class. Okay, so let's take a look at this graph. Now down here we have time, but time isn't linear. How do I say? It's kind of like logarithmic. So 10 to the negative 45th, is that a small number or a big number? Small number, very good. Over here, 10 to the 15th, big or small? Very big. And actually, the units are in seconds down here, but I'm going to kind of show you that if you take 10 to the 15th seconds, so that's like a 1 with 15 zeros after it, if you do the factor label on it, you'll get to actually, that is about 13.8, 13.7 billion years. 10 to the 15th seconds. It's true. I've done it before. I'm like, are you serious? Yes. So anyway, so look what's on the y-axis, temperature. So up here we have very hot conditions, 10 to the 32nd. Okay, and these units are in Kelvin units. Very hot. So now, if you might be, so if this is today, you're like, well, what is the temperature today? Okay, well, we're about, we talked about absolute zero in here, didn't we? So we're about, I think, 3 degrees Kelvin. Now that's not the temperature of our Earth, thank goodness, because that's very cold. But 3 degrees Kelvin is about the temperature of our universe. Because this is our universe. Okay, what do we got here? So it was very hot and very dense, and it began cooling down, okay? And you're like, well, how come it cooled down? Well, and actually we see this in meteorology. As the universe expanded, and actually as air expands, it cools down. It just does. Okay, you can think of it as, remember we talked about this has more potential energy, this has less. Okay, so some of that kinetic energy is converted to potential energy. It cools down. So it cools down, it gets larger, it cools down. Okay, so actually the way this scale works then is if this is like 10 to the negative 5th, so that's 0.00001 seconds, right there-ish. This is 10 to the 5th. This one right here is 10 to the 0th. Anybody know what 10 to the 0th is? 1. Anything raised to the 0th power. I don't know. 10 to the 0th is 1. Okay, yep. So this is 1 second after the Big Bang. So that's kind of putting things in perspective. It's kind of a strange sort of curve. And I already mentioned 10 to the 15th. I kind of lied a little bit. So if you go beyond 10 to the 15th to 4 times 10 to the 17th, then you get nowadays-ish. Okay. Now, one of the things I put on the board the other day was E is equal to mc squared. Okay, anytime you have an equivalency sign between two quantities, you're like, they must be related. Not only are they related, but we know that you can actually go back and forth between the two. So I'm going to try to talk you through this idea when the universe was very small, very dense, very hot. We had a lot of this. In physical science or in chemistry, a lot of times we use what we call reaction arrows, reactants go to form products. But if you see a two-way reaction arrow, that means it's going back and forth. Things like that happen all the time. So let's kind of take a look at what this would look like. And actually, some of these pictures some of my favorite pictures to talk about this coincide with some of OpenStack's favorite pictures. So some of these are redundant. You're going to see this here in a minute. But you've probably heard of antimatter, and you're like, oh, dude, you're so sci-fi-ish. But antimatter is really a thing, okay? And I don't have any videos to show you, but the way it worked is early on in our universe, there was equal amounts of matter and antimatter formed. Now, see, and again, I don't know the physics of it, but antimatter is a dangerous thing, but anyway, just like the sci-fi would say. But here we've talked about squiggles before. These squiggles could be kind of squiggles we saw with energy associated with our sun. So here we have energy early on in our solar system, energy early on in our universe actually being converted to matter, an electron and an anti-electron. And as it turned out, or what can happen here is the matter actually is turned into energy. So we have energy turned into matter, matter turned into energy. And it was just a crazy sort of time. Crazy time to be alive early on in our universe's history. Okay. This is, I mentioned the particle collider before, I think, in here. This is there are different particle colliders. This is the LHC, the Large Hadron Collider in France. And it may not look very big, but that actually is a city right there. And so it's very big, and it's, if you get, I think I might have showed a little bit of documentary about this. It's like a tunnel, you know, like a tunnel where nobody goes, right? It's very clean and all this. It was down for repair at one point. I don't know if it's still down for repair. So it's this humongous tunnel that has, I think it has magnets that help control the speed and the direction of the subatomic particles that they want to collide. So picture basically, if this is where they start the particles and it's called an accelerator on purpose because they accelerate the particles, go faster and faster. And I think what they do is they actually, the particles will cross each other, okay, and they'll keep making loops until they want them to collide. They allow them to collide, and it's kind of like, I've heard it, like if you want to know how a car is made and you have no other way, you can run that car into a brick wall and look at the pieces. That's kind of what a particle collider does. So in here, you know, we're all about protons and neutrons and electrons, which is awesome. But there are even smaller particles than that. And so that's kind of what a particle collider does. And so as we are understanding more about subatomic particles, we understand more about the particles that would have been present at the time of shortly after our universe was born. So again, this is kind of like, this is the same figure as I just showed you a minute ago. You can kind of see the open stacks thing right here. We have energy going to matter and matter going to form energy. So we're going to talk about different phases, like different stages of our universe's life. And we're going to see a lot of stages happened very early on. And now we're kind of, we are in the era of galaxies. How beautiful is that, right? But one of the stages we're going to talk about is this one. And this might look familiar. Well, maybe not. This is saying where a proton and a neutron go to form, this is the stage of nuclei. What's in the center of an atom, the nucleus of an atom, you would tell me protons and neutrons. So here we have subatomic particles kind of settling down to form helium. 3 minutes after. A lot of things happen between here and there. Okay, 300,000 to 700,000 years. This is the age of atoms. So what's that little minus thing there? Electrons, yep. And the P is protons. So here actually we see atoms kind of finally form. So what number, I feel like a magician, what number did I tell you to write down? It's going to be your quiz today. 380,000 years, yeah. So that's when we say actually the atoms, the electrons begin associated with the nuclei of atoms. So otherwise electrons are just crazy. They're just getting in the way of energy. So, you know, I mentioned the train wreck, sort of, or train wreck, the car wreck, so you can go backwards. Well, in order to understand the conditions at the time of our universe unfolding, we can look at the conditions now. And the conditions now, we have these 4 forces. We have the force of gravity. Some of these you may not aren't everyday forces. Gravity, an everyday force. Electromagnetism, might be more everyday than you think. Electromagnetism, hard to say. Think of something that's negatively charged and positively charged. What do they want to do? They want to come together. Okay, that's electromagnetic force. And actually we have that in every cute little atom, because you guys would tell me you have protons in the center of the atom, we have electrons outside. So every little atom has this important electromagnetic force. These other two are a little more elusive. The strong force and the weak force. They're very elusive, if you ask me. Strong force actually has to do with the center of an atom, and it has to do with the way, because you would tell me the nucleus of an atom is kind of complicated. Nucleus of an atom, you have protons and neutrons, and actually they don't necessarily want to coexist, but they do. There's a strong force binding them together. And then the weak force, weak force is similar. It has to do with the atom. Strong force, strong weak force. So those four forces we have today, and I actually, if you gravity, electromagnetism, kind of got that. Strong and weak have to do with the atom itself. So those we have today, and we had to kind of understand how those forces were here at the time that are of the Big Bang. So at high temperatures, which singularity, high temperatures, high density, yeah. At high temperatures, actually, and this was an Einstein thing, they call it the unified force. They think all four of those forces, gravity, electromagnetism, strong force, and weak force, actually were one unified force. Now I'm gonna, some of this stuff, and this is one of them, I'm just gonna kind of tell you what I've read. And then we're gonna see actually of those forces, the unified force, let's see, make sure I get this right. Of those four forces, then one breaks out and another breaks out. Bless you, and I can't remember which one it is. Super force, one breaks out, you have a gut force, another breaks out, you have electroweak force, and then last but not least, all four are themselves. And I didn't put any of this on the test this semester. But I'm going to go through the slides as if it is on the test. So the way you read this, again, this would be a universe unfolding here, and then over here, this is today. And so we see actually this would be the unified force, and then we have the gut force with these three, okay, and then we have the electroweak force with these two. So it's kind of a cool little figure showing you how they are together. But again, so what do you think? 10 to the negative fifth, we have all four forces. How is that time relative to 1 second after the Big Bang? Is it before or after? It is before. Yep, that was my whole point there. So a lot of stuff happened here. So let's talk eras. And if you're a dinosaur person, you kind of like the whole dinosaur, the eras of prehistoric eras. That's what it kind of reminds me of. So the first eras are going to be broken out by forces. So we have the Planck force. I'm sorry, this is kind of hard to see. Let's see if there's anything I need to tell you about. So the Planck era actually would be the Big Bang to when the forces were unified. And I think you kind of see the question mark up there. Definitely a question mark. Time-wise, let's see when the next era began. I think it's like 10 to the minus 43rd or something like that. Now the gut era kind of was what I was talking about a minute ago, where one breaks free. I think it must be maybe gravity breaks free. We still have electromagnetic, bless you, the strong and the weak force together. And up here, it's hard to see, but I have, 10 to the negative 43rd seconds was when gravity broke away. Pretty cool. Electroweak was when we actually lost the strong force. And this is kind of trying to give you a sense of magnitude. Now these are, the next set of eras are defined by particles. We actually kind of looked a little bit at this with some of the OpenStax figures a minute ago. Let's see. The particle era says elementary particles filled the universe, then quarks combined to make protons and antiprotons. Exciting times. Again, we're at a time of 10 to the minus, I can't read that, 13. So as I walk through these, what's happening to the temperature of the universe? Getting cooler. The universe is expanding and it's getting cooler. Cooler is important. Nucleosynthesis, what do you think is happening then? Yeah. The little nuclei are being formed. Isn't that adorable? Yes, I'm sorry, but I just think that's adorable. And what two particles are in the nucleus? Yeah, protons and neutrons. Yep. Cool. Now, this is no small thing, and I'm not saying I can tell you how, but we had the whole matter and antimatter sort of duking it out. Matter and antimatter duking it out. Reminds me of some Star Trek episodes where they go to these planets that all look alike, they're cheesy, and you know they have matter. But anyway, cool. Nucleosynthesis, era of the nuclei. Dun dun dun. Okay, so nucleosynthesis means the nuclei being formed. Era of the nuclei. This actually talks about the helium nuclei, which one's more complicated, helium or hydrogen? Helium's more complicated, so that's pretty exciting. And then after the era of nuclei, we get the era of the atoms. Now, this is exciting times. Do you kind of see where the red here, this is red and this is blue. The red here is kind of trying to tell you fuzzy. The red is fuzzy. The thing that makes it fuzzy is the electrons were kind of just not associated with the nuclei. So what date did I have you write down? You guys don't still get this on your final. 380,000 years. So after 380,000 years, the universe was expanding, cooled down enough so that now actually electrons go ahead and associate with their nuclei, and you have cute little atoms. Yay! Here in a minute, I am going to talk just a little bit about this background energy, background radiation. What's a little bit longer radiation than, which one is? So we have visible. What's longer than visible?
Infrared.
Infrared, thank you. What's longer than infrared?
Gamma.
What's that?
Gamma ray? Or is it X-ray?
No, X-rays are over here. So what's longer wavelength? No, gamma's over here. So those are short. I want long.
Microwave.
Yeah, see, I can't remember microwaves and then radio waves. I get those two mixed up. I was hoping somebody would come through for me. So we okay? So yep, so we have visible, infrared, microwaves, and then radio waves. They keep getting longer and longer. And over here, after visible, we have, what happened after visible? Shorter wavelength than visible. Ultraviolet, yep. X-rays and gamma rays, thank you. That she was cheating. That's not cheating.
I was cheating. I have it in my notes.
All right. So what era are we in today? It's not our test, but the galaxies. That goes along with the movie.
Are any of these errors on the test?
What's that?
Are any of these errors on the test?
Errors? No, I don't think so. I don't think it's on your review sheet. I thought you said, are any of these errors on the test? I'm like, oh,
Well,
not.
I'm sure there might be some of those, but-
Yeah. So we are, we're in the era of galaxies. Sigh. So here's how OpenStax kind of, with a little less detail, maybe kind of sums up all of that. Again, you have time. We have short time after the Big Bang. And remember, so this is going to be nowadays. So forces are unified here. Then they break apart. Forces break apart. Radiation. What's another name for radiation, you think? In E is equal to mc squared. E mc squared. Which one of those sound like radiation to you? Would it be the E, the M, or the C? Energy, as I was after. Radiation or energy. Yep. Energy dominates. Protons and antiprotons form. Electrons and positrons form. Okay, and then they unite to form atoms. Oh, that's my favorite. Yay! And then galaxies form. Okay, and stars form. Now, I'm not sure. I'm kind of like, galaxies form, then stars form? I'm like, really? Well, I suppose. I'm not sure. Anyway. And then today. I'm not going to call OpenStax about it. So I want to talk a little bit about that time. Yep, that time. Okay, this is when it was so chaotic. Okay, and then actually these little particles are the electrons, and the bigger things are the nuclei. And so at the era of atoms, doesn't that just look so nice and organized? Yep. So when we talk about looking for this kind of, how do I put it this way? If we look back in time, if we try to see anything back here, we can't, because energy, it's not a black hole, but energy can't escape because it just gets all, I don't know if you can see the zigzags. The energy zigzags. It's kind of like the random walk. It just zigzags, can't find its way out. So we actually talk about this time as the universe becoming transparent. So this time right here, not only was it time in order for those electrons to find their nuclei, but it had to be a certain coolness. So what temperature did I tell you our temperature is now? About how many Kelvin? We're about 3. We're about 3 Kelvin. It was about 3,000 Kelvin back when this happened, our universe temperature. Yeah, right now we're about 2.73. Now that is very cold. That's colder than Pluto. So that's the temperature of the universe. All right. So I'm going to talk about something, and this didn't make it to your test either, but it's an important thing called the cosmic microwave. See, are microwaves long or short? They are long. Yeah, the cosmic microwave background, but they're a little bit shorter than radio waves, right? Radio, micro, infrared, visible. Cosmic microwave background. As it turns out, if you take the temperature of 273 Kelvin and you, see, is it applying a redshift? I think it must be applying a redshift too. And you go far away, about 3 points to our cosmological horizon, which would be what, 13.7 or 13.8 billion light years away, you can actually, this little energy that we see coming from that far away is in the microwave region of the electromagnetic spectrum. That's my point. So what you're looking at here is this actually should be what our fingerprint of the, right after the universe became transparent, what those energies should look like. And it is kind of. This is new for me. OpenStack says this would be the Big Bang. It kind of seems kind of like it's getting smaller, but it's really not. It's expanding. Here we have temperatures cooling down. Of course, this would be the age of today. And this right here when it becomes transparent, and that is the 380,000 years after the Big Bang, when electrons settle down and energy actually could start to flow in all directions. And your authors kind of liken it to, if it's a cloudy day, okay, the way clouds work is clouds are just water droplets. You probably know that. Clouds are specifically water droplets in their liquid state. So in their liquid state, they you can't see beyond the cloud, depending upon thickness of the cloud. You know, different types of cloud, but it's like a nice thick one. But when those liquid water droplets then disperse, okay, into their gaseous state, then you can see in the same areas they were. I'll buy that analogy a little bit. Okay, so there are some stories that I think are worth telling, and this is one of them. So I'll let this video talk about how they came up with this cosmic microwave background. It involves pigeons, so how awesome is that? So I mentioned 3 gizmos. Here are the names of the gizmos. So we have the COBE, the WMAP, and the Planck. Those are 3 spacecraft that were created just to look for this kind of cosmic microwave background. Now, this actually is a map of like the distribution of the signal of the energy that was released right after the universe became transparent, about 380,000 years after the Big Bang. There they are in all their glory. Okay. And the caption says that they were actually got a standing ovation. Now, what we do in science a lot of times is we have a theoretical trend that we expect. The theoretical trend is red. The data that they got from, I don't know which one, Kobe, is the little boxes. So actually that's two sets of data, the theoretical and the actual experimental. And if they coincide like that, they get all of it. And people think, are you sure that's really how it happened? So here we see the 3 different gizmos out there, all looking. Now this is a map. Now we say the map of the universe, but actually it's the map of the universe from our perspective. You know, we still are limited to how far that we can see. So I'm going to go ahead and put this up here. There's no test question this semester over it. But if I were to ask you what's the most abundant element in the universe, you would say, what's the simplest one? Hydrogen. Yep. And then what comes after hydrogen? Helium. And actually, if you, what they've done is look at how much hydrogen and helium, it's called abundance, what the abundance of hydrogen and helium are in their universe now, and they can kind of backtrack to having it make sense for their model of, when we're talking about nucleosynthesis and all that stuff. And it fits. Bottom line is it fits. I mentioned inflation, that didn't make it to the test this semester either. But inflation was actually, we know the universe is expanding and its expansion is accelerating. But even closer back to the time of the Big Bang, our universe took a jump from being this big to being that big. It's called inflation. And during inflation, we kind of had these little perturbations that actually, you figure, we're talking little universe, those perturbations are going to become galaxies. And within those perturbations, then we have other little ding things that are within the galaxies going to become stars. So this is talking about inflation. This red one would be the standard model with no inflation. And this blue one here explains more where we had, it went from being this big to being this big. See, this is a radius along the y-axis. Now this one really kind of, we have an ant here. Now if you're an ant, you really can't, your size relative to the balloon is pretty small, which is kind of our size relative to the universe. So when the universe expands, or when the balloon expands, the ant can't tell. So when the universe expands, we can't tell. So this is again talking about singularity. All the matter that makes our universe was very hot and dense, means it's squished together. Here we have inflation. This is talking about how parts A and B that used to be close together at the time, shortly after the Big Bang, actually then came apart, okay? And they actually have similar characteristics, even though they're far apart. It kind of reminds me of, if you look at plate tectonics, that the Antarctic actually has similar characteristics of South America. Now this actually, I don't have a lot to add about this. This is talking about critical density and kind of what shape might our universe be. If it's if we're right at critical density, it's flat. A little more or a little less, it kind of takes different shapes. So I don't know, that confuses me. There's nothing on the test about that. About that. Move to the last slide. But there is something on your test about this. Okay. So I'm going to play this video, and it's the same video we watched the other day, but instead of looking at, I can't remember why I showed it the other day, but I want you to look at it in a sort of a different light. It's the one that says, why are the skies dark at night? So I'm going to play it again. So in science or in philosophy, we use this idea of paradox. And a paradox is a way to kind of think through things. So for instance, Olber's paradox says that It takes the kind of the anti of what we see. Now, our nighttime skies are dark. Okay, so we talked about that. This is the sun. Okay, if I'm the Earth, okay, we have daytime and we have nighttime. So nighttime here. Okay, the skies are dark. Now, according to Olber's paradox, the skies would not be dark. Look at it this way. What if all of the stars, okay, what if the stars didn't have lives? Because we talk about stars live their lives. They die and they do different things, depending on how massive they are. What if stars were always, okay? We know that it takes light a long time to get to us, but stars are always. So I'm going to go clear out here. I'm going to go 15 billion light years away. Stars are always. Okay, so stars were always, so 15 billion light years away. That light is going to kind of get to the Earth. It's going to get to the Earth. Because stars are always. I could go 20 billion light years away. Again, stars. Right? But, okay, so if stars never changed, okay, if our universe was infinite, okay, and if our universe was everywhere, we would, as we have our nighttime away from the sun, it'd be just like daytime. Because you give enough time, and it's infinite, that light's going to get to us. Okay.
So does that mean, like, in 3 billion years, if we're still here, that the sky will be bright at night, since we'll get more stars appearing?
I think the video, that's a good question. That's a really good question. I think the video is going to address that, and it's going to say that you said if we give it more time, well, the thing is that stars live lives. The stars, this kind of addresses something that we talked about before. In another billion years, some of those stars will have lived their lives and they're no longer shining. And so and they were replaced by stars that do. So we kind of have maybe think of it as kind of a constant amount. So that's a good question. So since it's not dark at night, either the universe has a limited number of stars, and I would say the universe. Now, to me, when it says the universe changes, to me, that just means that stars are living their lives. Stars are doing their star thing. Okay? The universe is changing. Stars go through cycles. And they're not infinite. They are finite. So, with that in mind, that's Olber's paradox. And that will be on your test. I think it's going to be a vocab question. So if you want to put vocab, you can. Olber's paradox. So let's take one more look at this.
I'm Jenny, and I quit smoking with
Hi, Jenny.
pancakes. It takes a lot of planning to be a smoker. It's like, when am I going to be able to sneak? Why?